Good afternoon, everyone. I would like to welcome all of you to today's webinar, Unlocking CCU Potential Through Electrochemistry. The webinar is hosted by the Waterproof Project. My name is Dusica Banduka. I'm from the nova-Institut. We are based in Western Germany and an independent consultancy. And within the Waterproof Project, we are responsible for the communication and dissemination, but also for the LCA and social LCA. I'm working on this project with my colleague Anke Schwarzenberger, who you will meet later. Just to give you a quick introduction on Waterproof. Waterproof is short for urban waste and water treatment emission reduction by utilizing CO2 for the production of formate-derived chemicals. As mentioned, it is an EU-funded project. We will end in May of 26. And our goal is to develop an electrochemical process that will convert CO2 emissions captured from waste incineration and wastewater treatment facilities into formic acid. We have identified 3 applications where we will test the derived formic acid, which will be cleaning detergents, the tanning of fish leather apparel, and also the development of acidic deputatic solvents called ADES, which are used to recover precious metals from waste incineration ash. The project also involves the assessment of social acceptance and sustainability impact of the developed solutions, which will be done in the LCA and social LCA. But we also have a Colombian partner on board where we'll develop strategies for the transferability to other urban communities in developing countries like Colombia. Here you can see an overview of all waterproof partners involved. This would be Avantium, Coatima, CTA, Ecover left us lately, Funditech, HVC, ADES, Nordic Fish Leather, Technalia, and Waternet. For today's webinar, we are super excited to welcome 3 expert speakers who were so kind to join us. We have Dr. Patrick Loeb from the Fraunhofer IMM. We have Brian Rawls from Avantium, who is also part of the Waterproof Consortium. And we have Danny Hellebusch from 12. You will first hear all 3 presentations in a row, each 20 minutes. And at the very end, we will have the opportunity to ask questions. For this purpose, please use the Q&A section in the menu line, and please address the specific speaker with @speaker. In the following days, we will also make the webinar slides and the recording of the webinar available on the website. And if you want to stay up to date, we also highly recommend signing up for the Waterproof newsletter. And now my colleague Anke Schwarzenberger will give an introduction to our first speaker.
Yes, exactly. So our first speaker, as Dusica already said, is Patrick Loeb. He holds a PhD in chemistry from the University of Heidelberg here in Germany. He is now leader of the group Flow Chemistry and the deputy head of the division chemistry at the Fraunhofer Institute for Microengineering and Microsystems in Mainz, also in Germany. At the IMM, he develops, realizes, and supports the application of microstructured flow reactors to improve chemical production processes for the industry. In this case, mainly fine chemicals, specialty chemicals, and pharmaceutical industry. He's author and co-author of various publications, particularly in the fields of process engineering, application of microstructured components with organic synthesis, and flow chemistry. And with this, I would like to hand over to Patrick to present the first presentation.
So I hope now you should see
we can see
my
it
presentation.
Fine. Thank you.
Okay, that's fine. So yes, okay. I have to thank for the invitation to join this webinar with a presentation, and I'm happy that I can report about a Fraunhofer internal project. So this will be the starting point of my presentation. And I entitled my presentation Flow Reactors for the Electrochemical Carbon Dioxide Reduction to Formate Formic Acid and Beyond, because I would like to give also an outlook above the works we have done in this specific project I will mention. So I'm part, as mentioned, of Fraunhofer IMM, and Fraunhofer IMM is part of the Fraunhofer Gesellschaft. And Fraunhofer Gesellschaft is the largest research organization for applied research and development services. So we receive some public funding, but our task is also to support industry in implementing innovations. Yeah, as very brief introduction. And it's very important for me. The results I will show are part result of a larger project, and I will give the acknowledgements in my last slide. But to explain a little bit also Fraunhofer, the project background, because as mentioned, Fraunhofer is an organization for applied research and development services, especially with public funding partly, but also we have to support industry. Yeah, but from time to time we pick up also within Fraunhofer. We are about more than 70 institutes, so there are from time to time internal lighthouse so-called lighthouse projects, which pick up strategic important points for economy, society, or scientifically. And the speciality about this project, this internal project, is that they allow to bring the expertise together of different institutes. So the 70 institutes are not all working on electrochemistry. One is on polymer processing, the other one on biotechnology, and the other one on reactor technology as ourselves. Yeah? So the decisive thing here is that to bring in these projects together the expertise of the different institutes and generate therefrom a good starting point for implementation in the market or support for industry. And the specific project I'm talking about is the so-called SHAPE IT project, shaping the future of green chemistry by process intensification and digitalization. And it ended mid of last year. And as mentioned, we have involved a row of Fraunhofer institutes, and I listed them here. And I have been project leader at the IMM for our specific working force. And again, allow me this additional introduction. It's really the idea of pooling the expertise of different players together. That's similar like an EU project, only that we combine our activities within Fraunhofer to reach central targets. And so the project was motivated by helping especially chemical pharmaceutical industry to address the challenges they have, like global competition, time to market, increase of efficiency, sustainability, and also naturally our overall aims of coming to a circular economy, greenhouse gases neutrality, defossilization of production processes. So, and the ambition of the project was also as to pool these expertises and to have also a one-stop contact point if industry have questions in this regard over this Fraunhofer project and community. But let's come now closer to the technical topic. So we see that we have to move to a more sustainable society. Yeah, that means we have to use more renewable materials for the manufacturing industry. And if you look especially at the polymer production industry, we have a production volume of 400 million tons worldwide in 2021, and the largest share produced so far from fossil resources. So also here is the trend to move to renewable feedstock bases, which may come from mechanical or chemical recycling of plastic materials, biomass, or the topic today of CO2. And CO2 naturally has the advantage as raw material being available, having a high scalability and sustainability potential. If you look at the CO2 usage for polymer production, a very brief overview. You have different approaches here. Certainly you will hear also today different approaches. You have for example, just to give a few examples, you have the direct reaction of CO2 with epoxides to form polycarbonates. Then you have the synthesis of traditional or new monomer through a reactive conversion of CO2. This might be going to methanol, followed then by the methanol to propylene, a process into naturally propylene. And we have the process targeting more within SHAPE IT, we targeted a more complex and valuable polymer building blocks, and that's what I will report on. You see the dimensional literature citation, but that's very important because this allows me to report you quite in detail about our efforts. and it's a joint publication of all involved Fraunhofer Institute. It's open access. You're invited to have a look on it. So, what was the specialty about our activities within the SHAPE-IT project? So we developed a novel process cascade, combining the advantages of electrochemical CO₂ conversion with the synthetic potential of industrial biotechnology. And so we have several steps: the electrocatalytic reduction of CO₂ to formic acid, and the formic acid is then used as substrate for a fermentation process, delivering diaminopentane, the cadaverine, via L-lysine as precursor. Then, naturally, to come, we want to use it in a polycondensation process. You have a need for downstream processing, reaching a high purity. Then you have this usage of the monomer in the polycondensation process to produce a specific polyamide materials. So, as mentioned, the SHAPE-IT project, it's important that you have that the partners, Fraunhofer partners, bringing expertise along this process chain. So it's important. It's not only about the electroreduction, but it's also considering the following steps. And for example, just to mention, you see here the different steps: electrochemistry, biotechnology, downstream processing, polycondensation, and why we have selected diaminopentane, because it's an interesting monomer, but not accessible in larger amounts currently from conventional petroleum-based sources. And then it's also an interesting monomer to get novel polymer structures with properties not so described so far. Now coming closer to the electrochemistry, since it's a process chain, naturally, the electrochemistry approach we are taking, the process condition, the cell concept we are using, depends on the following step, because we are not looking at the reduction as a standalone process, because then it's alkaline conditions are favorable, but we want to use the produced mixture directly in the fermentation process, and then it's like that alkaline catalytes based on potassium hydroxide or potassium carbonate are incompatible with the fermentation process. So it's necessary either to design catalyst material more suited for less alkaline regimes, or to have novel process regimes and novel reactors concepts. So, and in the project, we have looked at two cell configurations, and out of process schemes, and one is using, as commonly used, a liquid catalyte in the combination with a phosphate buffer. And you see here the cell configuration, and to give some, the cell we have used for our investigation, to give some more details here, we have an anode with an iridium mixed metal oxide from a commercial supplier, special anode. Then we have 1.6 millimeter thick compartments, cathode area and area of 120 square centimeter, and we have a gas diffusion layer from Freudenberg, and this was done but coated internally by Fraunhofer IGB, and this is a tin-based electrocatalyst, and we have a cation exchange membrane. And so this was one process option we explored, and here you see some selected results. So we managed we reach a current density up to 18 milliampere per square centimeter, and we reached a molar concentration of the formate of almost 1 molar as final concentration in our experiments. And you see that we are quite a constant Faraday efficiency over the process time. And so this was the one approach here. And in the context of the project, it was also a little bit checking out other process alternatives. And what I mentioned, it's good that we can use the produced formic acid directly in the fermentation process. And then, as mentioned, catalyte salts negatively impacting the fermentation process. So one idea was to use a catalyte-free process. And this catalyte-free process is described by Kitty Park from the Korean Institute of Energy Research in 2018. And that was a little bit our starting point to design a corresponding electrochemical cell for our investigations. So the advantage, we have a formic acid solution free of electrolyte salts, which are advantageous as feed stream for fermentation. And the cell configuration looks then like this. We have also zero gap cathodic and anodic half cells. And the decisive point is instead of that's perhaps to point out, to instead of an liquid catalyte, also where we have to dissolve the CO2, we use more or less CO2 with evaporated water. So the water just is a little bit coating our gas diffusion electrode. And so we have small amounts of water in the system, and we have an improved in difference to a liquid catalyte, we improve the mass transfer properties. So this is the decisive point in the cell configuration. So what so we realized within I will go in the following slide, I will show some details of this electrochemical cell, because this was a little bit my focus and the focus of the Institute IMM. And so before showing you the details, we have started experimentation. So we have set it in operation. As you see, we have not ended up with this is the stand from the last year. We are working still on the topic, and we have not published more results so far due to confidentiality reasons. But we ended up there to establish the system. We produce formic acid and formate in a high concentration without salts. And we underlined a little bit the potential. And so we have seen no loss of formic acid formate by diffusion in the analyte. We have stable process parameters. We see that we can influence the performance of the cell by tuning CO2 and water vapor ratio. And it's clear that with a Faraday efficiency of 12%, we have to make further studies. But for this, our reactor is now in place and our settings are done. To point a little bit out, what was the motivation? What is the potential behind this approach? So what we have reached, we had reached about also 1 molar. Also, to point out a little bit potential we have with this approach is if you look in the publication from Kitty Park, he ended up, for example, with 40 grams of formate per liter, also 1 molar solution roughly, with a partial current density of around 50 milliampere per square centimeter, a Faraday efficiency above 90%, and at a low salted voltage of 2.2 volt. So, and he also calculated energy efficient and other parameters at best mounted up to 65%. And he used commercial tin catalysts. What we have in the project, we developed also our own catalyst, and so catalyst variation is also still a point of investigation in our case. So, but what I want to focus a little bit on is to show you a little bit the cell configuration we used. What you see here is the electrochemical cell we developed for the project, having an electrode area of around 50 square centimeters in this range. You see on the light, the cathode on the left is the cathode current collector. On this is put then the gas diffusion electrode, and in the middle you see the added membrane, and on the right then you see the anodic current collector with this electrode, the mesh anode put on it. And so we have integrated heat exchangers, and so you can combine these two halves and have your electrochemical reactor. So, and I want to point out, we specifically designed this electrochemical reactor. This was Fraunhofer IMM part. So if we have an atom, I just want to put outline a little bit the realization of the reactor technology. So we use additive manufacturing to produce the cone collector plates, the basic raw plates, with the internal fluid distribution structure for heat exchange, but also of a catalyte supply or water vapor supply. We generated channels, microchannels, a fluid distribution system on a smooth surface by milling. We have some surface coating with Teflon on the plates. In some parts, we have to remove the polymer coating then again, and from the periphery, and then to have an electric contact of the electrodes. And then some parts we even made galvanic deposition of platinum on the free metal surfaces for better electric contact and corrosion protection. So this is just a point I want to outline, that we spent quite a lot of engineering efforts in this reactor type. And you see here's the electrochemical reactor we used then in our lab scale investigations. You see the two black half cells and embedded in a joint press. Yeah, so you have no screwing. So you have you put these cells together by this press. And this is the crossover point to broadening a little view. And the design already reflects a bit later scale up. So instead of using one cell package, you can add more cell packages in this press. Yeah? And this is a concept we introduced already some years ago. And you here see the original type of reactor concept. And you see clearly that the before was a derivation of this one you see here now. And as mentioned the basic idea is to have the cell stack within this press. And here are some more parameters given. So the electrode surface about 40 square centimeter, small electrode distance is possible, and the basic, and you can put in this press up to 20 cells. So the general concept is to use a single cell for first lab scale investigations, but then if you have to first scale up, to just add more cells and then to come to a pilot scale. So the reactor concept already foresees a certain type of scale up. I just want to mention that the concept is naturally open not only for CO2 reduction. Yeah, so we modify it always to the specific applications. So we have used it for the cation flow method. We have used it for peroxide decarbonate synthesis. We have CC coupling of phenols investigated, and also cold electrolysis. And a later point example I just want to mention, because with this cold electrolysis, we evaluated a scale-up approach. So we see we used in one experiment 2 cells, and in the other one 4. And you see that the productivity increased by doubling of the numbers, while all the other process parameters are kept constant, also Faraday efficiency, conversion selectivity. And this is just to underline that's a basic approach also within the formic acid idea, to use it there. And to give you an idea about the scale we reached here, we have been a production rate of about we have tested up to 10 cells in parallel, and then we ended up with 1.4 kilogram per hour of fatty acids in the cold electrolysis. So to close my presentation, you see, I want to bridge a little bit to screening. And if you see the same reactor concept, we have used also for an industrial customer, HTE, to provide them screening cells. And you see also in this picture, although you see here, this is a screening setup for electrochemistry, background so far water electrolysis. But you see that this press with 4 cells, screening cells, have been implemented in this plant. So why is it worth mentioning also in context of CO2? Also here you see our electrochemical cell we developed in this context, and the press again. Naturally, if you look at the business opportunities, I think if you look at screening, then certainly water electrolysis naturally is a good topic, and the other one is naturally CO2 conversion. Yeah? So it's also feasible to use these approaches for CO2 reactions, conversion reactions in screening. To sum up, although I have shown you a little bit that we integrated in the SHAPE-IT project an electrochemical CO₂ reduction process in a process cascade to deliver a novel green polymer. We explore this promising catalytic-free process route to formic acid, which would be very beneficial to follow it further. I showed you a little bit modular scalable reactor design behind, which we used for the formic acid production, but also for other applications, and that you can use such approach also for screening purposes. And with that, oh yes, I have now come to a very important slide. As mentioned, I want to point out again that the works on the formic acid process change up to the polymer was work of a large team within Fraunhofer, involving different Fraunhofer institutes. And naturally, all the works on the electrochemistry in-house at IMM is also belonging to a team, especially Athanasios Tsiorkas as senior scientist for electrochemistry. What I like to point out, this Fraunhofer Lighthouse project is also supporting a little bit the idea that the single Fraunhofer institutes join together also to address inquiries from outside of Fraunhofer as one-stop shop, and this is the Fraunhofer Chemistry Alliance, and where we try to address topics which are above the level of single institutes. And finally, I want to thank you for your attention, and I'm looking forward, although I'm eager to see the other presentations and their perspective on CO₂ usage. Thanks.
Thank you very much, Patrick. I will stop your screen sharing, or you can do it yourself, so the other speakers can start presenting. And with that, I'm looking forward to introduce our next speaker, who would be Brian Rawls from Avantium, specifically the Volta group. Brian earned his master's degree in environmental technology from Wageningen University in 2018, where he performed research on bioelectrochemical systems for CO₂ conversion. Since then, he continued his passion for electrochemical research at Avantium, contributing to the development of the Volta technology. Currently, Brian serves as the principal researcher in the Waterproof project and also in the Vivaldi, which is also an EU-funded project, which seek to valorize formic acid as an appealing eco2RR product. Take it away, Brian. Thank you for joining today.
Yes, thank you for that introduction. Let's see, I'm going to share my screen here. Does that look okay for the audience?
We don't see anything yet.
Oh, you don't see anything yet. Okay, let me try that again. Let's see. How about that?
This looks promising, yes.
Okay, good, good. Okay, let's see. Hold on a sec. Oops. Okay. Yes. So hi, I'm Brian Rawls from Avantium, and today I'll give a dual topic presentation. They both relate quite closely to each other. So that's an introduction to the Waterproof project, specifically on the electrochemical CO₂ conversion into formic acid, and Avantium's electrochemical production of CO₂-based polyesters and chemicals. Just a quick introduction to my company, Avantium. We are a company based in the Netherlands. Our headquarters is in Amsterdam. We are a medium-sized chemical technology company, about 280 employees. We're most well known for our bio-based polymer division. So that's it's called PEF. It's a bio-based PET alternative. We're currently scaling that up to a commercial plant in the north of the Netherlands. And the group that I'm in, which I'll give more information on, is the Volta group. We are a electrochemistry group converting CO₂ into chemicals and polyesters. So, and the Volta group is involved in the Waterproof project. So here's a kind of a flow diagram of what the Waterproof technology seeks to do. So starting from the left, we have our two CO₂ producers from wastewater treatment and municipal waste. Those both produce CO2, which will be used by our group to do the electrochemical CO2 reduction into formic acid. And then the formic acid produced from the electrochemical conversions will go to multiple different applications from consumer products, leather tanning, and deep eutectic solvent metal extraction. And the idea is that all of that carbon is distributed back into the waste and wastewater segments. So there's that circular carbon cycle embedded in this technology. Looking more closely at the CO2 conversion technology. So here we have a diagram of what is actually going through in the system. So first we have the electrochemical CO2 reduction reaction, where CO2 is converted into potassium formate. It's the salt of formic acid. On the anode side, we are working with a company that is going to do water oxidation to hydrogen peroxide, which finds its applications in wastewater treatment. Once the formate is produced, we convert that salt into the acid via electrodialysis, and that will be going to downstream separations for the end use applications in this project. In order to recycle the electrolyte, in this case, the potassium, we're going to use a recycling loop. It's the bicarbonation reaction, where we convert KOH and CO2 into the electrolyte that's used for the CO2 reduction step. That's potassium bicarbonate. So why do we want to do CO2 reduction? Why is that a relevant technology? Well, first off, it is a CCU technology, so it valorizes CO2 as a feedstock. It reduces our societal demand on fossil carbon. It is quite abundant in our atmosphere, and it's apparent that we need to remove it from the atmosphere. And what's nice about this technology is it's an electrochemical conversion, so we have the potential to couple it with renewable electricity sources. And in terms of the low temperature electrochemical CO2 reduction, there is quite a broad range of products that can be produced here. So in this graph below, I show all of the different products that can be produced and their mass energy demands. So the amount of energy it takes to convert CO2 into that respective product. And you can see as you go down the list, you have more electrons that need to be put into these products, and therefore you're more and more reduced products. And what happens is you lose more and more mass as you reduce these products into the C1, C2 compounds that are, require lots of energy for the mass that they produce. So in Volta, we focus on the top 3 products that come from this reaction. So oxalate, formate, and carbon monoxide, as these are the ideal CO2 reduction products, as they require the least amount of energy for the mass that they obtain. So getting into our CO2 valorization routes. So our main route in Volta is to do this electrochemical CO2 conversion, first to formate. With formate, we couple that in a thermochemical reaction to potassium oxalate. And the potassium oxalate is then converted into its acid and reduced via hydrogenation into glycolic acid. And the glycolic acid can be used as a CO2-based polyester. That's called polylactic coglycolic acid. And that is our main product. It's a polyester that directly comes from CO2. But in the waterproof project, we have an offshoot technology of this, of our main route. So we convert formate to formic acid via electrodialysis. And we have 2 EU projects, waterproof and iconic, where we do this do this work in. So formic acid can be used as a drop-in for the existing formic acid market. However, that is a small market, so we're looking into emerging applications for formic acid, and those two projects are targeted that. So Volta, we are involved in this mid-stage research. So if you look in terms of the technology readiness level scale, you have the 1 to 4 level, which is mostly academic research. We mostly work in this 4 to 7, 4 to 8 range, where we're doing the lab scale research, the applied research, and then developing and deploying that technology to various CO2 emitters and users of our products. So the waterproof project is a great example of how we're getting closer to that commercialization of this technology. So currently, the electrochemical CO2 reduction reaction to formate is approximately a TRL5. I mean, that's debatable, but somewhere in this mid-stage development. Waterproof aims to develop that to our TRL7, which is defined as our, in our scales and production targets that we're achieving. But what are some of the technology milestones that need to be achieved for this TRL9 commercialization of this technology? So from various techno-economic assessments that we've done within our group and our partners, we've identified the top 5 technology milestones for this commercialization. So the first one, developing electrodes with high selectivity at high current density. The value that I put at that is greater than 90% selectivity at 200 milliamps per square centimeter. So that's also, probably a benchmark for the industry. I put that the industry status is green because I think that there's a lot of academic research focused on catalysis and at these high currents. So that is something that's very well explored in academia. Something that's less explored in the academic research is the conversion efficiency. So in terms of how much CO2 are they actually using in their system? What's the efficiency of that system? Also in terms of the energy, I put that as a yellow because I think there is opportunity to optimize that efficiency, but it's just an underexplored topic. Another very important aspect of this technology is the high product concentration. So achieving for example, greater than 20% concentration in the liquid and gas streams, depending on which product you're obtaining. I think I've seen a lot of reports that have shown that that's possible. So I put that as green. But then when it comes to the last 2 topics, these are the least explored topics that need the most attention to commercialize this, and that's electrode lifetime and scalability. And those have not been demonstrated to a broad extent. So I put those as red because there's very few players in that tackling that problem. So which electrodes do we use for CO2 reduction? So there's a challenge when you're doing gas electrochemistry is that you have poor solubility in aqueous systems and you have quite a low diffusivity. So therefore your mass transport is poor. And that's why in Volta, we choose to go for gas diffusion electrodes because they circumvent this issue of mass transport. So this is also something that's, I think a lot of companies and a lot of academic researchers have kind of honed in on GDEs as the top tier electrode configuration for CO2 reduction. And there is clear reasons why we have a lot of technology development from hydrogen and fuel cell production that use these electrodes for their conversions. So, however, with GDEs, it becomes quite tricky to scale these electrodes. Because they have this low pressure drop, they're very porous. They tend, if you work with a liquid electrolyte, you often have a problem when you scale up your cell that your hydrostatic pressure coming from your cell, so the liquid pressure that is exerted on the electrode, is often greater than the pressure drop of the GDE itself. So you can see as we scaled from our 10 square centimeter cell all the way up to our 0.2 square meter cell, we noticed some interesting things happening with the flow properties of our GDE. So what we see is that as you have a 2 meter high electrode, you have a hydrostatic pressure regime, low at the top and high at the bottom. And what happens is that the CO2, the gas, has a preferential pathway toward the top. So some things that need to be improved here are cell or GDE engineering to improve this distribution of gas evenly throughout your GDE. That's something that we're working in the waterproof project to improve on. So currently our approach to scaling electrochemical cells is we do a lot of research at the 10 to 100 centimeters squared size. That's especially made for catalyst and GDE work. And we first scale these electrodes vertically to the 0.1 and 0.2 square meter says in a single cell. That allows us to study the flow properties at elevated heights. With this configuration figured out, then we can scale out the cells in a stacked configuration, which is modular. You can vary the amount of cells you have in your stack, which increases the area of the electrode without requiring larger electrodes. And some inspiration we get from this approach is from the chloralkali industry, where they use GDEs in the oxygen depolarized cathode. So here is a industrial example of the scales of GDEs that have already been applied in industry. Another very important aspect of CO2 reduction is the product separation. I alluded to this before in my presentation, but just an interesting fact that I found in literature is that one report said that about approximately 50% of total production cost is attributed to the separations in bio-based chemicals and fuels. So therefore, it's an incredibly important topic that does not get as much attention as needed, and especially if you're producing a liquid soluble product, as we are, and making potassium formate and formic acid. So those high product concentrations are very important. What you can see in this graph below is that I graphed the blue line is showing the amount of energy it takes to remove water from a formic acid stream. And then on the x-axis is its respective concentration. So you can see that as you go to more and more concentrated electrolytes, your energy demand gets lower and lower. And in the waterproof project, we're aiming for approximately 20 weight percent formate, as we think that this is a realistic process target for this concentration. And yeah, so we're looking at improving this efficiency by looking at different innovative separations of formic acid from this aqueous stream. And we're also exploring the opportunity of microbial conversion. So that was something that Patrick alluded to in his project about maybe directly feeding this into a microbial thing where you don't need to go to this concentrated regime of formic acid where it requires so much energy to just make a concentrated product. So where are we now and where would we like to go? So Volta We've finished multiple projects on CO2 to formate. One we did in 2023, that was the Ocean project. We did demonstrated a single cell operation at 0.2 square meters, where we produced a quarter of a kilo an hour. And we ran this off-site at a at a power plant for 5,000 hours. And currently we're in the waterproof project, where we aim to stack that single cell to a total area of 1 square meter, reaching a total production rate of 1.5 kilos per hour of formate. And in that demonstrator, we also are going to demonstrate the product separation and salt recovery of that stream. This next project that we just engaged in is called Iconic, where we aim to further scale this technology to a total cell area of 1 square meter and in a stacked configuration. And this is nearing our pilot demonstrator scale. So that's where we are now as Volta. And with that, we are a team of about 20 scientists and engineers working hard on this technology. And we could not do it without the help of our grant projects. So Waterproof, Hiccups, and Iconic are our main grant projects. So thank you to our funding partners for that. And yes, we'll take questions at the other time. So thank you.
Yes, thank you very much, Brian. That was a very nice overview of waterproof and the related projects, Hiccups and Iconic. And I would like to ask you to close your presentation now, because we will have the Q&A at the end of the last talk, which will be given by Danny Hellebusch from 12. So I would like to introduce you. The title of your talk will be Demonstration of 12's Revolutionary Industrial Photosynthesis Technology, which 12 has successfully scaled up to transform CO2 into products ranging from sustainable aviation fuel to car components. On the speaker himself, Danny Hellebusch, has spent over 15 years working in the green, clean, and climate tech space, ranging from academic research to startups. He earned his PhD from UC Berkeley under the guidance of Paul Alivisatos. Sorry for mispronouncing maybe. During his graduate work, he studied how to engineer nanocrystals for optoelectronic applications with a focus on photovoltaics. Since graduating, then he has worked for a few startups ranging from products such as drop-in solar cell components, ultra-thin printed batteries, and now carbon utilization with 12. So, Danny, the floor is yours, please.
Thank you so much. Happy to be here. I'm honored to have been invited. Again, my name is Danny Hellebusch. I lead the CO2 electrolysis group at 12, which is responsible for doing the early stage development work all the way to scaling and deploying our electrolyzers. Again, representing 12, we bill ourselves as a carbon transformation company, kind of focusing first on carbon dioxide to jet fuel. I'll be kind of going at a higher level here. This is less, probably more on sort of the business approach versus more the science. And I think there's a lot of academic literature about what we've been doing. So ultimately, what is 12 doing here? We're similar goals as what the other speakers have kind of communicated here. We're trying to take renewable electricity, carbon dioxide, and water, and convert it to basic building blocks, which then can be fed downstream and target a myriad of products. And so the slide here is kind of showing sort of when we did the kind of a market exploration, what we can do with our CO2 electrolysis technology here. We kind of have this sort of Opus box, this sort of the name of our containerized electrolyzer. This is kind of a computer-generated image here, but kind of going down here, we have anything from polycarbonates, which we demonstrated with a partnership with a fashion brand called Pangaya. And we also did demonstrate some polyurethane, some other components. But as we kind of looked where the product market fit is best for us, we identified that jet fuel as one of the industries that's hardest to decarbonize due to, it's hard to electrify planes at the moment with the current status with batteries, for example. And we also find the market is large enough to then raise money to then start to fund the scaling of our technology. So that kind of tasks us with the idea of how do we take our CO2 electrolysis and then build a plant to generate jet fuel. And so we kind of, this thing called an airplane concept here, where we have our, let me get my cursor here. Nope, where I don't usually do this as much, but yeah, so if we have our CO2, here it is. Our core technology here is still our CO2 electrolyzer. We're able to actually tune that to output carbon monoxide. And so we can feed carbon dioxide from biogenic or direct air capture sources, water and renewable electricity, or low carbon electricity sources into our electrolyzer. And then we can also feed it into a water electrolyzer, which there are plenty of options kind of almost off the shelf at this point. And then by having the hydrogen and the carbon monoxide, sort of an electronic version of that, we have a syngas. And from there, we can build out sort of the back end, which has been pretty well established, which usually is Fischer-Tropsch process. Then we do kind of then there's a hydrofracker and as well as a fractionator to then, which can be tuned to create a range of e-fuels, including our e-jet product, as well as e-marine for marine vessels, and as well as the e-diesel for trucking, for example. The other output here is e-naphtha, which it can be, naphtha is a building block for the supply chain for a lot of other these sort of durable plastic goods. Again, Tool's trying to avoid sort of the single-use plastic use case, but looking for things like they'll be used for 10, 20 years, such as car components, for example. So kind of like, how do we go from our plant concept in our lab scale here? So one thing that 12 has benefited is we are a PEM-based CO2 electrolysis. So we have basically decades of research we kind of piggyback in terms of like thinking about durability of the reactor components, as well as a lot of the electrochemistry and physics that go into our product here. And here's a picture of Plug's electrolyzer. That's kind of more of a recent picture from their development. And I'm trying to go from this sort of like containerized concept. I think Brian also has some pictures of this sort of idea as well on his photo for the formate, CO2 to formate. So we're kind of all have a very similar graphics and pictures of this kind of shipping container here. And I'll kind of show you some pictures where we have our progress towards that. So once we kind of have our plan and sort of our goals of like what size we want, we have to think about what are the key metrics of our CO2 electrolyzer that we need to focus on in order to make the plant economics of our jet plant, essentially. So we kind of focus on sort of OpEx and CapEx. OpEx is short for operating expense, and then CapEx is for capital expense. And we kind of break down a lot of the metrics of our electrolyzer and which ones are levers to tune and of course lower the cost of both of these. And so we have a kind of cross-section picture of our generic cell concept here. Again, not going to kind of go into like the details there. We look at like ferritic yield, voltage efficiency, as well as CO2 utilization are a few of the levers we can use to optimize the operating expense. So kind of keeping those kind of feed into the energy efficiency. But then we think about the capital expenditure. So how can we get as much CO generated per electrolyzer? There's a lot of balance of stack that we have to take into account as well. And that's where current density, lifetime, how long the stacks last, as well as, again, CO2 utilization is also a part component of that as well. So once we kind of have our metrics, we then go into we kind of spend a lot of time at the lab scale, optimizing our CO2 electrolyzer here. And so on the left here is examples of how we kind of did a lot of optimization on the catalyst coating of the membrane. Just an example of various parameters, temperature of our coating process. We do use a spray process at the moment, nozzle type, frequency, flow rates, and there's just a few. There's probably a few dozen we had to optimize. An example of sort of how we're fitting curves, looking for the optimal morphology and microstructure of that catalyst layer. Kind of here in the middle is sort of just an example of some top-down SEM images showing how we can change parameters and get different sort of like texture of the top of the catalyst layer, which we then correlate with cross sections to get an idea what the actual morphology is throughout the layer. In parallel, for like tuning the microstructure over catalyst layer is also the operating conditions here. And so an example of a few of those operating conditions is sort of like the inlet analyte temperature, the CO2 flow rate, compression, and again, a few other dozen ones, kind of how you start up as well. And again, this plot here is an example of, you know, how we optimize the operating conditions here. So this is a simple one where we kind of just increase flow rate, lower CO2 flow rate, and you can see the Faraday yield is quite sensitive to this as well as voltage. You can see this, the low CO2 flow rate, you get kind of a short cell life. So once we kind of have at the subscale, kind of optimize our materials, and I think again the Brian mentioned like you kind of do a lot of the materials and GDE optimization at the subscale. Then once we kind of lock in and demonstrate sort of at the bench, we're able to kind of show that to investors, get more, and then we can start the scaling process to go towards our kind of jet plant concept. So looking here is a few kind of show how we went from our coating process, so the MEA. It's kind of like the core part of our electrolyzer. As we start here at the bench, and this is a spray coating machine. It's roughly the size of maybe a dishwasher or a small oven. It sits in the bench top. I mean, this is where we were able to do a lot of those optimizations for the spray coating, you know, get the right texture, right morphology, for example. And this is an example of inside the machine where we have our MEAs kind of fixed to the surface there. And once we kind of got our spray process locked in, then we were able to kind of like translate that, work with the manufacturer of this equipment to make sort of a pilot line of how we can kind of show like a semi-continuous line where we can make MEAs reliably and at a full scale. And so at the bottom here, we spent a lot of time kind of designing this sort of conveyorized system where it has two spray booths. We have two spray steps in our MEA, and we have sort of a conveyorized system. So we can kind of separate where before we had both steps in the one box, we're able to separate those for kind of for like a more higher throughput process. Then we can once we scale our manufacturing process, this is where we will multiply these for the appropriate capacity that we need. Above here is a example of inside the booth. So you can see now we have two nozzles. There's two lanes. This last picture here is a picture for engineers, kind of proudly showing off one of the first full-scale MEAs that we produced at 12 a few years ago. So in parallel to scaling the MEA, we have to scale our reactor. And so you'll see similarities again with what a lot of people are doing. You know, we small concept, make it bigger, then you start stacking. So kind of at the very far left here, you have our 25 centimeters, you know, single cell reactor. We have the gas, the reactants and product inputs and outputs. And we kind of did a first scaling here. We went from 25 to 100 centimeters squared. It's a simple 4x area, still a single cell. There we had to kind of identify what might be problematic in terms of like, you know, coding uniformities between those two. But the 100 cell allowed us to start exploring stacking and sort of scaling the technology here. And from, you know, down below here, we kind of had our initial, almost like prototype of an electrolyzer that was kind of stuffed in here. And that's where we used to generate enough CO that we could demonstrate various products. For example, that's where we partnered with people to make polycarbonate, as well as a jet fuel with the Air Force. And this is a picture of a typical, you know, test station we have for this. Picture should probably be actually under here. I apologize for that. So once we did find that product market fit, we start to talk about scaling to a commercially relevant size. This is where we look at sort of the greater than 750 square centimeter product. And we first start with our single cell, and this is a picture of the you know, it's stack size, but just a single cell, and therefore we kind of understand sort of flow distribution issues at that single cell. Again, isolating at that single cell. But once we have that figured out, we start stacking and figuring out like what problems we have with our flow distribution with more and more cells. And this is a picture of one of our first 100 cell stacks here on our sort of product size test station, which is roughly the size of a shipping container as well. And once we got here, this is when we start to like break ground with our E-jet fuel facility up at Moses Lake, Washington, which we fed initially with hydroelectric, which is plentiful up in the Pacific Northwest of the United States. And so I'm kind of show you kind of a little bit under the hood of how we think about we had to do a lot of electrochemical correlation and making sure that we can tune our lab scale to be predictive of our large format. And the importance of this is we got to be as resource efficient at the lab scale, and so we can optimize there and predict the large format. There are things we can't predict. For example, a lot of the flow channels, for example, large format are just hard to mimic at the lab scale. And this is just an example of some electrochemical data here showing how we translated sort of our lab scale single cell performance to our kind of large format single cell MEA here. And the red and blue kind of just repeats so that the data can be noisy. There's a lot of, you get a larger area, you used to have a lot more quality issues, which I'll kind of speak about later, which we had to focus on. And then once you do like the single cell, and you also have to translate that single cell to the multiple cell stacks. We typically didn't go directly from single cell to a tall stack. We typically went, 5, then 50, 100, kind of like a scaling exercise. And again, some electrochemical data showing that we spent a lot of time kind of making sure they match, because we like to be predictive at the most resource efficient size as possible. So then you can imagine that the single cell subscale, what is size independent, and things that are size dependent, how we can understand how this translates for each of these scales. So it's kind of an overview of the process we kind of built up of our pilot facility down here in the Bay Area. And so I kind of showed examples of sort of our MEA pilot line, which can produce enough MEAs such to produce, to support the building of these 100-cell stacks, as well as we have a bunch of like a stack pilot assembly line where we kind of assemble all the subcomponents and then we kit them up and then stack them into these very large stacks. As it's a lot of process control, a lot of quality control. We found that both those were key once we got to larger and larger stacks. This is so kind of another thing though is once you're building 100-cell stacks, and you have about 10 to 20 in rotation, you have a lot of parts. You got to actually build out a supply chain to help build relationships with vendors, and also talk about drawings and what are the critical to quality parts of those, have them meet them, and also internally inspect them. That's kind of where it became really, really important as we scaled to more and more cells. We spent a lot of the last year to building that sort of muscle here at 12. Understanding what are the critical quality parts on, like, for example, a flow field. You could measure, you can really waste a lot of time measuring every single aspect of it, but really got to figure out what are the single ones that are, what are the, 2 or 3 things you can measure efficiently that will be predictive of a high quality stack. And so that's where we built a supply chain team out. We built a quality control team out to help us with this and all the measurements. And then of course we have the MEA coding, and there's a lot of quality aspects of there, like when you're making, hundreds and hundreds of MEAs, you have to build up, what defects are acceptable, which defects are problematic for lifetime, kind of going back to those metrics. And then you kind of have a stack assembly. And here's a picture of our team kind of in a clean room. And that's also a good example where, like, how clean does the room need to be, to prevent the particles from getting on an O-ring seal, for example. And then you have sort of the stack installation. Before we ship the stacks, we do electrochemical testing. We have a few tests that we do to be predictive of what the stack will, how the stack will behave once it's installed in the plant. So again, the last 4 years since I've joined 12, it's been sort of lab scale to the larger scale, or commercially relevant scale. I mean, really proud of all the work the team has done to kind of realize sort of a commercially relevant CO2 electrolyzer system here. And again, here's a picture of our 100-cell stack, and then you kind of see a picture of one of our, basically it's our electrolyzer balancer stack, as we call it, being installed at our Alameda facility. But we have essentially clones of these being installed up at our Lake Moses site. So kind of like to summarize where we've come here. So we kind of start at the single cell, thinking about what are the design requirements we need to meet that jet fuel market, and how we start to take that, optimize sort of the materials and some of the reactor components, build up the stack, and then start to design the balance of stack that's appropriate for our jet fuel plant, and sort of now launching it into this facility up at Moses Lake. On the backdrop here, a little grayed out, is actually a 3D rendering of our Moses Lake site, kind of showing showing the flow from our CO2 electrolyzers. And I'll apologize. I don't have the plant memorized here, but I believe the Fischer-Tropsch unit is here, and I'm not sure the bottling is, but I'll have to make sure I talk to Andre about that. But we actually have it being built. I don't have any pictures of the progress. We have a lot of the flares already installed. We have a lot of the process piping is being installed. So we're really excited for that to be launched. And so our our team has done a lot of analysis to make sure that we're like actually realizing our goal of reducing carbon emissions. And so we've done analysis showing that our e-jet product does in fact will lower the CO2 emissions about 90% compared to conventional jet fuel. We've already struck agreements with some pretty well-known airline consortiums, Alaska Airlines, AIG, Etihad. The advantage, though, of the CO2 electrolysis pathway compared to other things such as the biofuels pathways, we don't have as many water or land issues, so we don't have to compete with agriculture or other environmental uses. And we have this kind of validated by the U.S. Air Force, so it's drop-in and ready to go. So the intent here is, trying to launch a new industry around this jet fuel product, and hopefully we can expand again to realize other aspects such as like the plastic goods. And so kind of spent it's been a long time in the past 5 years, sort of like the lab scale, learning how to stack, building out sort of that whole process in the supply chain. And then we kind of had that's our Opus 1 system. We're kind of a smaller scale. Our Opus 2 is sort of the one that we were able to deploy to our air plant. And right now we're kind of in this sort of air plant industrial deployment as we have our demonstration site. And then next year we are scheduled to be producing jet fuel and have regular flights on Alaska Airlines. And moving forward will be sort of the growth and scale. We'll build more of the plants and build them more efficiently, both at a time and cost perspective. Thanks again for listening to me today. We have a bunch of press releases here. You can kind of look us up if you want to learn more about what 12 has been doing. Once again, thank you, and I'll stop the screen share.
Thank you very much, Danny. So before we continue, I would just like to quickly mention that the Waterproof project will be present with an exhibition booth at the CO2-based Fuels and Chemicals conference, where some of you from the audience might also be interested in submitting a poster. Poster submissions are still open for a couple of days. And it also includes an innovation award, which 12 actually won 2 years ago with specifically the product that you just were introduced to. So we would be happy to see some of you over there. And we have some questions in the Q&A section, and this is your opportunity to also add some few. We also encourage the other speakers, if you have questions to each other, don't be shy, add them to the Q&A. And then I would just start reading them out. The first one goes directly to Danny. How did you determine the optimization size of a cell? Do you plan to go bigger than 25 square centimeters?
The question's about how do we arrive at 25 square centimeters for our subscale or our lab scale?
I think they want to know if you plan to go bigger any time soon.
Yeah, we're already greater than 750 square centimeters. So that 100 cell stack is roughly the size on cross section.
Thank you very much. The second one is also for you. Which instruments do you use? How do you do the quality control part? Which measurements? Which are the defects? Do you have problems with particles, for example?
So we talk about quality control, the incoming parts. So we typically have several components that come in, and we have sort of dimensional analysis. So the stack mechanical design engineers kind of have an idealized design and sort of tolerances around that. And we use a series of electronic measurements as well as hand tools to check certain key parts, such as thickness or roughness spec, is an example of some of our flow fields that we'll measure. In terms of particle contamination, we do have an issue, but we have a pretty rigorous cleaning process that we had to develop. So we had to take our stack components, and when we develop the process, clean them various detergents and other things, and ship them out to external parties to validate what the particle count is on, and the contamination of other materials of the stack parts.
Thank you. You did also touch on this in your presentation. I guess for people that want to look it up again. Joel Tickner is asking, do you have any estimates of potential for growth in CO₂-based polymers to replace petrochemical-based ones? Any thoughts on what would be needed to accelerate scale? Maybe this could go to Brian and Patrick, as 12 are already a bit advanced in their process. Would anyone like to take this one? I think Brian mentioned polymers in his presentation as well, right?
I did, yeah, because we're developing a new polymer from our CO₂ reduction to, yeah. So it's PLGA, which is a new market. It is an existing polymer in the biopolymer space, but it is relatively limited market. So we're looking to kind of replace some of those petrochemical existing polymers, but that can be quite challenging to break into that market. Yeah.
Would you like to add something, Patrick? No?
I think I remember that we at least have done a basic cost calculation. I think, but I'm not sure, not for the electrochemistry step alone, but up to the monomer or even the polymer. And I think then naturally we're quite early in our development stage. So, yeah, so a lot of assumptions are there in, but I think we compare that we would be in the same range at the upper limit of conventional products. Yeah, but it's a high functionality naturally on current electricity price. So that's naturally decisive, one of the decisive income parameters. Yeah. But especially we have selected a special polymer, so not a conventional one. Yeah.
Thank you. And commercial feasibility seems to be the topic of interest for the following questions as well. How much higher is commercial product scale from CO₂ versus fossil fuel origin now in future projection? And Tom Grenstrom also would like to know, could all of you say something about the cost effectiveness of the end products? I guess these two go hand in hand. Would anyone like to start? Maybe you, Danny, as you are already working with clients that might have considered this.
Yeah, so our demonstration plan at Moses Lake is like we'll be selling the jet fuel. It's also has a stack of a bunch of incentives here in the United States, as well as state incentives to be cost competitive with the fossil drive thing. We do anticipate over the next like 5 to 10 years as we phased out. But right now we're trying to introduce the thing, introduce the capability or the demonstration, and start to focus. Once we show that people are willing to buy it at that price point, we can start to come down the cost curve. And for example is our MEAs are probably an order of magnitude too costly, but we're still kind of in the R&D phase. But we have roadmaps to come down the cost curves. And usually when you introduce technologies, you kind of come at the R&D cost, kind of just want to get that product market fit, and then the cost curve typically the exponential decay down as you sort of swap out components over the 5-year timeline. That's kind of that's my experience from other introducing other technologies, is they're not meant to be cost effective right off the bat. But our projections and our economic analysis does show we can get cost competitive over that timeline, about 5 to 10 years.
Thank you. And maybe the other two as well, as both of you are looking into projects producing formic acid to be applied in consumer products where price competitiveness is a huge issue.
Yeah, so formic acid is a difficult one because that's very cost competitive. So that's why we're not really targeting drop-in chemicals, because they're so cost competitive with the fossil counterparts. We're going for the high-end polymer space where we can have a little bit more freedom to operate with in terms of costs, because I mean, as a R&D staged chemical process, we're definitely at the high end of that costs, and it takes time for us to develop this technology. Also, we have to compete with these legacy technologies.
Would you like to add something, Patrick?
I just rechecked. We have really looked at this cost scenario of the principal economic viability up to the diaminopentane. So really not only on the formic acid production, but also the following fermentation step. And for this process, then it's important to have really a highly concentrated formic acid, salt-free, that you have no process cleaning process in between electrolysis and the fermentation process. And in this configuration with high yields, and then we would have a reasonable price. But from the time scale, we have not optimized the process so far, but it would come to a reasonable price, let's say it this way. Yeah.
Thank you. And I would keep it with you. So the next question is for the formic acid in biological routes. What's the concentration of formic acid that you use in biological processes? How does the acidity of formic acid affect the microorganisms? Addressing Patrick.
A good question. Let me see. I'm not sure if I can answer you the question directly because I'm not involved in a follow-up process.
Would you like a minute to prepare?
Yeah, if you give me a minute, then I can cross-check a little.
And I'll take the next one, which is, all three of you addressed it, but is the transfer from lab to production scale-up seamless? People hope it would be, but I guess maybe someone would like to elaborate on that. I think Brian already mentioned plenty of issues, or at least critical options connected with this task, but maybe you would like to say something.
Yeah, certainly not. I mean, it's yeah, you've got all different aspects to consider with scaling, and that's no easy feat.
What was your main challenge, Danny, when you went to scale up?
Yeah, I mean, for us, there was a lot. We kind of had an initial stack design hypothesis, and what we found is when we scaled it, not all the quality aspects were taken into account initially. It was almost like an R&D mindset applied to industrial things. So we spent a lot of time sort of reworking the design over and over to make sure that we define the tolerances well. And those kind of translate to like flow distribution issues. We had problems getting the gas and to equally distribute amongst all the cells. So we had to kind of keep refining to make sure refine the design to get that equal distribution, because as you need all the cells are operating in series. If you have one cell that has too high a voltage, you can kind of the whole stack is no longer working, and you have to kind of take it down so you can max out in the voltage and be unsafe to operate.
So it's adjustments basically all along the way with each scale up. The next question would also be for you. What is the EJet capacity of the first plant? Do you need to add aromatics to your EJet to make it consistent with the fuel-derived fuels? Fossil fuels, apologies.
Oh no, all good. I'm trying. I don't know if it's public. This is where I'm more in the technical trenches. I can check the scale of that thing. I'm not sure. We'll probably be announcing it at some press release end of this year or early next year, the actual size. But unfortunately, I don't make sure. I'll just kind of keep that for now, just be safe for 12. But in terms of the aromatics, yeah. So this is again where I'm not an expert in the the deployment. That's more on the plant side and sort of the commercial side. But what I do know is our initial launch will be blending the fuel with 50-50 with a conventional jet to get those aromatics. But my understanding is that the airline industry is moving, actually, I think it's a simple chain. Like the aromatics usually help with a lot of the seals in the jet engine. So I think that they are updating the planes over time to take the synthetic aviation fuels. And that's another thing is it's not just sustainable, but sometimes you can call them synthetic if you're not actually, the carbon intensity score is not good. You can use it with gray CO or even gray hydrogen, but it's an issue for any synthetic fuel.
So one of our participants states that fossil-derived fuels and chemicals are so cheap that they will never be beaten by, for example, e-jet. But the real comparison would be bio-derived molecules. So how do the presenters see the competition of CO2 electrolysis versus biochemical processes, cost versus scale considered?
I think I can take this one. Yeah, that's a pretty interesting comparison there, I think. So I mean, we're looking at still two different feedstocks from biomass or from CO2, and yeah, both are considered renewables. And I think the one advantage that e-fuels have is that they are, yeah, you can make them much more selectively with lower amount of side products in your stream. So from biomass, you have these complex feedstocks that often have lots of different side streams that you need to address. So I think that in terms of selectivity and efficiency, I think e-fuels can get really close to, or if not surpass, what biofuels can do.
That's interesting. I think this would not be everyone's first estimation of the situation. And Patrick, would you like to take the question, or should we add one more?
I would like to come back to the concentration of the formated fermentation process. I have a quick look at the publication. It was about 5 grams per liter. And what I remember that it was very decisive, the pH control for the fermentation process, just to see, because either it's entering the cell as formic acid or formate, and this is influenced by the pH. But I would like to give the reference to the literature, which is much more detailed. And since the fermentation process was not my core expertise.
Perfect. And then I would come to today's final question, which is addressing Danny. How does PEM-based CO production compare with solid oxide? Is solid oxide system for more efficient than PEM? And why did 12 choose PEM over solid oxide?
Mm-hmm. Yeah, so I think the person is recognizing that it comes down to like the voltage of solid oxide. They typically operate at a much higher temperature, and therefore that the upper potential is significantly lower, closer to the thermodynamic limit. And then 12 has chose to kind of do the lower temperature PEM-based one. There's a few advantages here. One is when we talk about deploying these in further beyond sort of initial EJET, they're actually that easier to integrate with the intermittent renewables. Low temperature PEM can be kind of cycled up and down as we might have sort of a surplus of renewable energy, for example. In addition, what we have found that is a solid oxide typically has, because it operates so high, it's a really high demand on the materials. And so the lifetime is not really proven out yet, where we can get significantly longer lifetime with our kind of low temperature PEM-based system, given that we are, paying a little bit of a tax on the additional voltage and efficiency, which we're, once we get it rolled out, that's a goal, is to kind of drive towards a lower voltage overall.
Thank you for answering. So I think we're coming to the end of today's webinar. Thanks to all speakers. Very nice that you gave us some insights into your processes and developments. And also thanks to all participants. As we mentioned previously, so the recording of today's webinar and the slides will be made available on the Waterproof website. And we also invite you to watch out for the next episodes, which will deal with CO2-derived chemicals. So maybe some of you will rejoin us. Thanks to everyone and hope to see you soon. Bye-bye.